Okay, so we're talking about spaces of topologies for mappings and sections of vector bundles. So we had talked last time, and the time before, about various classes of regularity. So I'll remind you what those are. All right, so we have covered, so we had things that are finitely differentiable, things that are finitely differentiable with Lipschitz top derivative, smooth things, real analytic things, and holomorphic things, and we had covered everything except for this, which is kind of the most elaborate to describe. So this is what we're talking about. So we're thinking about analytic mappings between two analytic manifolds M and N. So just to be clear, I will always say holomorphic when I mean complex analytic. And so when I say analytic, I always will mean real analytic. So analytic is real analytic. So we're talking about analytic mappings between analytic manifolds M and N. So remember last time, where we had gotten to was I had a subset A of a real analytic manifold M, and what I had done was I had talked about the set N bar A of neighborhoods. So this is neighborhoods U bar of M in M bar. Okay, so M bar here is a holomorphic extension of M. So it is a holomorphic manifold whose dimension, complex dimension, is the same as the real dimension of M. Okay, and M is contained in M bar as a totally real submanifold. So this is all stuff that I talked about last time. So I had this directed set N bar sub A of these are not neighborhoods of M, but they're neighborhoods of A. Okay, in M bar. Okay, and so if you choose a U bar in here, so a neighborhood of M in M bar, sorry, a neighborhood of A in M bar, then I had this, okay. So this is holomorphic mappings from the complex manifold U bar into the complex manifold N bar, which, when you restrict them to points in A, so those are the real points, they take values in N. Okay, so these are holomorphic extensions of mappings from A into N bar. All right, so we had one of these guys for each U bar in a neighborhood of A. Then we have a mapping from, right, so then what we did was we took the direct limit here. So we took, and I described this explicitly last time, so I'll just say quickly in words. If you have two neighborhoods here, let's say U bar and V bar, you say that a mapping in here with U bar and V bar, you say the two of those guys are equivalent when there's a smaller neighborhood on which both of those mappings agree. And so using that notion of equivalence, the set of equivalence classes we denoted by this. Okay. Then we have a bunch of mappings which go from here into here. Okay, so these mappings simply take a holomorphic mapping from U bar into N bar, let's say phi, okay, and sends it to its equivalence class. Right, so this is all stuff that we talked about last time. So these we would call the germs of holomorphic mappings about A. All right? Okay, so now each of these has a topology, okay, namely the compact open topology of the mappings that we have from U bar to N bar. So we talked about that before, and we can just restrict that topology to the holomorphic mappings, and it also restricts to the real holomorphic mappings. So you have nice topologies on each of these guys, and so what this gives you is a topology here, which is the final topology. So that is the finest I never remember whether it's coarsest or finest.
On the right, it's the strongest. On the left, it's the weakest.
Strongest means finest, okay? Yeah, good, thank you. I never remember that. Okay, so it's the finest topology, so that all of these inclusions are continuous, all right? So that gives us a topology here. All right, so we do this for every subset A of M. Now we're going to apply this construction in two special cases. And what we will get is two descriptions of topologies on the space of real analytic mappings. The first one I'll call the final topology, and it arises just simply from taking A to be equal to M. Okay, so then we have this, sorry, I need more stuff here. This is going to be A, and then I also need an N there. Actually, so I apologize again. This is the way I think I denoted this last time, was like that. Okay, mappings from N to N, and the germs are about A. Okay. All right. So then we have then a natural mapping. From C omega to space of germs. Okay, so we just apply this particular construction in the case where A is equal to M. So the germs of holomorphic mappings okay, defined in a neighborhood M in the holomorphic extension M bar. Okay, what is this mapping? So this mapping is just the mapping of holomorphic extension. Holomorphic. Okay, so I'm not going to go through this in detail. It's relatively, this is one of those things that's not deep. Okay, so here's how it goes. Take a real analytic mapping here, phi. Okay, so one of the things I told you last time is that given a real analytic mapping, there is some neighborhood of M in M bar, and a holomorphic extension from that neighborhood into N bar. Okay, so that gives us a thing whose germ we can take. Okay, so then you take the germ of that mapping. Okay, so the existence of the holomorphic extension gives you the definition of this mapping. Okay, and the fact that this mapping is a bijection is a consequence of the fact that, well, surjective is clear. If you have a germ here, that means just by definition it's the extension of a real analytic mapping defined on M. So that's surjectivity of that mapping. Injectivity of that mapping is a consequence of the fact that if you know a mapping from a neighborhood of M, a complex neighborhood of M into N bar, okay, that mapping is uniquely determined on any connected component. That's a property of holomorphic mappings. Okay, that's one of the rigidity properties of holomorphic mappings. Okay, so that gives you surjectivity and injectivity of this mapping. Okay, so germs of holomorphic extensions. That's what that mapping is. Okay, so this map is a bijection. And so we have the final topology. Okay, here, okay, because now defined by asking that the mappings, okay, so these now are mappings from C hol R, U bar, M bar, okay? All right, so by this construction here, there are mappings into M and M. Okay, and then I just told you that this is identified with that. Okay. So these mappings are should be continuous. Okay, and they should be continuous for every U bar in, okay, which is a neighborhood of M in M bar. Okay, so that's the final topology. All right, so that's one topology for this space. It's a very natural description. Unfortunately, it's very difficult to prove anything useful about this topology from that description. Okay, so the other description is more complex, or so it seems, but it at least allows you to say some things about the topology on this space. Okay, and this one, I'll call like this. Okay, so how does this one go? So here, we're going to again apply this construction, and what we're going to do is we're going to apply this construction for every compact set K of M. So we let K be compact. Okay, so then we have a countable subset Uj of the set of neighborhoods of K in M bar. Okay. And this is why compactness is important, because this countable that I'm about to state the existence of right now is not true for non-compact subsets of M. Okay? Okay, so it has this property of being cofinal, and this is a very slick way of saying that certain things are true when you talk about topologies, but let me just say what cofinal means. So what it means is that given a U bar in a neighborhood of K in M bar, there exists a capital N, a capital, yikes, I can't use anything. Let me just call it K, such that U bar is contained, U bar J is contained in U bar for every J greater than or equal to K. Okay? And the key thing here is the countability of this. And that's, so you can easily prove this assertion that I just made basically by definition of compactness. Okay? All right. So what that does in essence is it gives you some simpler properties of the final topology on here coming from these inclusions, because you can essentially only consider the countable subset of inclusions, that not restrictions, that you would have going from here to here.
Sorry, what is in K bar here?
It's the set of neighborhoods of K in M bar. Yeah. Okay. All right. So, and I will not be specific about this right now for two reasons. One reason is that in the case, with the level of generality that I'm now talking about, which is mappings from M into N, a lot of the things that I imagine are true, I don't actually know to be true. I know that they're true for sections of vector bundles. Okay, so there's still some work to be done to really flesh out the properties of this space. Okay, so these are the germs of mappings from M into N defined on neighborhoods of K. Okay, so all I want to say here is that countability of this cofinal subset of the set of neighborhoods gives some properties to this space that are not true for non-compact subsets of M, and in particular for M itself. Okay? All right, I'll say some things about this when we talk about sections of vector bundles. Okay? All right, so now, if M is second countable, which we're going to be assuming, as I think I mentioned at some point in the past lecture. Okay, so if M is second countable, we have a compact exhaustion. Okay, so remember that this means AJs are compact. Okay. The interior, Kj plus 1 is contained in the interior of Kj. Okay, so they, all right, do I have that backwards? Yes, sorry. I meant that. Okay, so they grow in a substantial way at each step. Okay, and of course M is the union of the Kj's. Okay, so that's what I mean by compact exhaustion. Okay, then, so there's two countable things happening here that make this topology, description of the topology nicer. One is here, and the other is here. Okay, so we have mappings. Okay, so now the mappings go from analytic mappings on M into these spaces of germs. Okay,
And
so
in your definition for cofinal,
yeah.
is that sequence dependent on U bar, or is it?
Well, the sequence doesn't depend on U bar at all. The sequence is chosen. Okay, then given a U bar, you can find a J.
No, not a subsequence. The sequence.
The sequence is chosen in the beginning. Okay, so the point is that for any neighborhood of K, I can find a J large enough so that Uj is contained in that neighborhood. So the neighborhoods somehow form kind of like a base for the set of neighborhoods of K in M bar. That's the idea, and that's where compactness comes in. Okay. Okay, so then we have mappings like this. So it takes a real analytic mapping from M into N, and it gives you a germ of holomorphic extensions around each of these Kj's. Okay, germs. Okay, so it's M, N, Kj. Okay, and this is elementary. Okay, so what I do is I take a mapping from an analytic mapping from M into N. I holomorphically extend it so that it's defined on some neighborhood U bar of M and going into N bar. Okay, that then gives me a germ here. Okay, just by taking germs, because a mapping which is from a neighborhood of M is also a neighborhood of Kj. Okay. All right, so then now what we have then is an initial topology, okay, because our mappings are now going that way. So this is going to be the coarsest topology on here, so that all of these mappings are continuous. Okay. Now, this is not, I believe, an elaborate conjecture. This is almost certainly true. It's true in some cases. All right, so I believe that the initial topology that I am just describing and the final topology that I just erased are the same. And I'll say a little tiny story about that. All right, so and so this is true in the case when you're talking about functions. Okay, so for real analytic functions, this is an old and difficult result of André Martineau from 1966. So how does he? So what he does here is he uses the fact that these initial and final topologies are locally convex. Okay, and so he proves, and so in that case, it's relatively easy to establish that there is a linear isomorphism between the two direct limits that you get. Well, between this, well, I mean, I already said it, between this and the set of holomorphic germs of mappings defined in neighborhoods of M. All right, so he establishes that you have that linear isomorphism. That's relatively straightforward. The difficult part is establishing that that's a homeomorphism, and he does that by using sort of general facts from functional analysis involving duality. So in previous work he had studied in great detail the dual of this space. Well, not quite this space actually, more like that space, okay? And he'd studied duals of germs, okay? So he had done a lot of work which allowed him then to prove that these two topologies agree. And this is almost certainly the topologies will almost certainly agree in the general case, and I'm imagining that it will be doable by embedding N into some large Euclidean space by Grauer's theorem. That's my guess about how you would prove that, but I just haven't done it yet, okay? So these things aren't actually studied at all presently, okay? Nobody talks about topologies on spaces of real analytic mappings between manifolds. Okay, so that gives us...
I think real meter talked about this topology.
Okay, yeah, but really, yeah, okay. So that gives us topologies for all of these cases. Oh, sorry. Okay, so we have topologies for all those spaces of mappings. Okay, so now what I'm going to do is I'm going to give you 3 alternative descriptions of these topologies. Okay, so why? Because after we have all of these topologies sort of in the bag, I'm going to be using them like crazy. All right. So my view is that one of the real contributions of all of this kind of analysis that we're talking about is that it allows you to talk about these things in a very unified way for all degrees of regularity. And so we'll see that when we start talking about how to use this stuff, okay? So I think it's really worth developing comprehensively the descriptions of these topologies, okay? Some of these descriptions are will allow us to say useful things about the properties of these topologies, for example. Okay, so right now all we have is topologies. We know really from the descriptions that I gave, sometimes you can say useful things about the topology, sometimes you can't, okay? But some of the descriptions that I'm going to give facilitate talking about things like, are these topologies complete in some way? Okay, are they separable? Things like that. Okay, so at this point we don't know a lot about these topologies, and so we want to be able to say something about it, and perhaps the best way is to consider these spaces as uniform spaces. Okay? Now, what do I mean by a uniform space? Well, if you've studied this, for example, by reading Bourbaki, then you know that there's three equivalent descriptions of uniformity. We will just take as our definition the most concrete of those three descriptions, and that is involving semimetrics. Okay? So given a topological space, T. So sorry, I don't even need that. I apologize. The whole point is that you have a topology. Okay, so I just have a set T, and what T has defined on it, a family dA, okay, of semimetrics. Okay, so each of these guys, the normal name for these is, or a common name for these is pseudometrics. However, we're going to be talking about cases of sections of vector bundles, and then they become seminorms, so it seems stupid to call one a seminorm and the other a pseudometric. They're serving exactly the same purpose, and semimetric is a name that's used, so I'm going to go with the less well-known, but still used terminology, semimetric. Okay, so this means they have every property except the distance between, if the distance between 2 points is 0, it's not necessarily the case that the 2 points agree. Okay, so that's what I mean by semimetric. Okay, so there's a topology on here whose subbase is the set of balls in the seminorms. Okay, so I have balls that are like, let's say, B, A, R. So let's see, so this is going to be the ball, let's see, for the 8th metric, I'm going to have a ball of radius R centered at a point X and T. This is going to be the set of all the Y's in T, such that D, A, X, Y, R. Okay, so the open sets in this topology then are arbitrary unions of finite intersections of those things. Okay? All right, so that defines, so this is what we will mean by a uniform structure. Okay? Okay, so what I'm going to do is I'm going to put a uniform structure on all of these things. Okay? And I will do that by defining these semimetrics. Okay, so how are we going to do this? Okay, so semimetrics are defined for a compact subset K of M. Okay, so associated with each compact subset K of M, I'm going to have a list of semimetrics, not a single semimetric, but a bunch of them. But the point is that I'm going to do a construction, and the construction I will do I will do for a fixed compact set K, and then one of the parameters in my index set, indexing the semimetrics, will be the compact set K. So depending on which case I'm talking about, there will be others. Okay? All right, so let's first look at the finitely differentiable case. Okay, so now remember, we had defined Riemannian metrics on the k-jets of this. Okay, so remember how we did that. Okay, so we did that by establishing a bijection between this space and this space. Okay. Right. So I indicated in fairly elaborate constructions using, so remember that this required me to choose affine connections on M and N and Riemannian metrics on M and N. Okay. Those Riemannian metrics induced by multilinearity, Riemannian metrics on the tensor powers of the cotangent bundle. Okay, so I had metrics on all of these vector bundles, and metrics on the vector bundles plus metrics on the guy downstairs gave me metrics on the total space here. Okay, so there's an elaborate construction that I outlined, so that's done. Okay, so I have Riemannian metrics on this coming from okay, so let me call this Riemannian metric G bar K, coming from Riemannian metrics on each of the components of this. Okay. So these were the symmetric tensor product, remember? Okay. Okay, so these ones I wrote like that. Okay. All right, and there's an important one little fact that I don't think when I defined these things I mentioned this, but it's kind of, there's a little tiny detail that I want to mention, not because it's so important in understanding this, but because it's important in making you realize that when we come to talking about the analytic case, there's something kind of deep going on there. Okay, so I want to give you the formula that relates those, and the formula is this. Okay, so it just has to do with how you put the, this is a direct sum, and so I just want to indicate how you put, how each of these GJs factors into the G bar K, and it, I'll sort of give you a abbreviated version of this formula. Okay. Like that. Okay, the thing I wanted to emphasize is that factor. Okay, it seems kind of unimportant right now, but that factor has to be there in order for the things that I'm going to say to make sense in the real analytic case. And this has to do with growth properties of derivatives of real analytic functions. Okay, I don't think I gave, the normal thing would be to just have this be, this factor not be there. And that definition works for all cases except the real analytic case. Okay. All right, so, sorry, that was a little detour. Now we'll go back to the finitely differentiable case. Okay, so what I'm going to do is I'm going to define d k m. Okay? So the index k is for the compact subset k. The superscript will refer to the degree of regularity. Okay, so things down below are indexes for the seminorms. Okay, and the things up above tell me what degree of regularity I'm working with. All right, so I have two mappings of two class CM mappings, phi and psi, from M to N, and here's the definition of what I mean by the distance between them. Okay, so this is soup. Okay. So now I have, corresponding to this Riemannian metric, I have a normal distance metric, just a metric space metric, which I'll write as dk. Okay, so this is dk of jk b of x, jk psi of x, okay, and x runs over k. Okay. All right, so that gives me a semi-metric. Okay, so this won't be a metric, of course, because you could easily have two mappings that agree on k, and therefore their distance would be 0 here, but the mappings wouldn't have to be the same. Okay. All right, so so that gives me the finitely differentiable case. So this is now, for I run k over all compact subsets, this gives me my family of semimetrics. Okay. In the Lipschitz case, I have now these guys. Okay, so these have the same definition as above. Okay, and that accounts for the CM part. Now I have to account for the Lipschitz part. Okay, and so remember that when we had talked about Lipschitz functions, we had this semi-metric for Lipschitzness, which we call dilatation. Okay, so we had d m plus lip, okay, over k. Okay. Is defined using dilatation. We had done this before, and I don't want to go back and repeat all of that because, well, first of all, I probably will make a mistake if I try to do everything in a concise way, and we had already done it before. Okay, dilatation. Okay, so I take these semimetrics and these semimetrics, which I had defined using dilatation. Okay, so these were kind of complicated. We had an embedding of a manifold into a space of Banach, a Banach space of functions and stuff. So it was kind of an elaborate construction, but we did it before. Okay, so you get, for each k, you have two semimetrics, this one and this one. Okay, in the smooth case, you have d k m infinity. Okay. And this has the more or less obvious definition. That's that. Okay, so the only difference now between this case is that m here is an index in my semimetric, okay? Because I'm now talking about infinitely differentiable things. But the definition of the semimetric is the same formula as that. All right. The holomorphic case. I can just remember that the holomorphic topology is just the compact open topology. Okay? And so the semimetrics are the semimetrics for the compact open topology, which are just the continuous versions, K. Okay? The C0 versions here. Okay? So those are semimetrics in the holomorphic case. And then finally, in the real analytic case, okay, so this one is more complicated. Okay, so we let C C0, we have this weird space. Okay, so this is sequences A in positive real numbers, and they have to converge to 0.
Sorry,
Yeah.
the question of the definition of this metric here.
This one?
Shouldn't the soup be also over little k in n, or?
No, no, no. I'm fixing a compact set K.
No, but the little k. There's a little k there, right?
Oh, sorry. I apologize. This is an M.
Ah.
Yeah, yeah. Because all the derivatives are contained in there, right?
Exactly.
Yeah. Thanks. Yeah.
Orders, right?
Yeah, and this is no, that's sorry. These are all M's. I apologize. Yeah, thanks. Does that answer your question?
So
This is the degree of
exactly.
Yeah. Okay. Yeah. Thanks. Okay. All right. So in the real analytic case, I have this subspace of positive sequences that converge to 0. Okay, now what are the semimetrics? So I have a semimetric. Okay. And the semimetric is indexed by a compact set K and one of these sequences. Okay. So it's d omega K A, okay, of B psi. Okay, so it's soup. All right, A0, A1 to AM, D M of J M B of X, J M psi of X. Okay. Okay, and this soup is over all M's, okay, and X's and K. All right, so there's already, even the definition of these things already contains an assumption, and that is that the supremum is finite for real analytic mappings phi and psi. There's no reason whatsoever, certainly for smooth functions, the supremum will not be finite. Okay? So it is a property of analytic mappings that this thing will be finite. Okay, so I'm already saying something when I write down this definition. And it's something non-trivial. Okay, and this is where the factors of J factorial in my definition of the Riemannian matrix comes in.
Is this directly from Cauchy estimates, basically?
Yeah, it involves Cauchy estimates. The connection between this and Cauchy estimates is really complicated.
I got it.
Actually,
It's not a one-one.
That's right, yeah. Okay, so we're done, right? So this is the uniform space description of mappings, okay? So thus, for each compact K in M plus some other data, depending on the degree of regularity, okay? So for the finitely differentiable Lipschitz case, there's no other data. Okay, in the smooth case, the other data is an integer m. And then in the analytic case, the other data is a sequence A of positive numbers converging to 0. Okay. And I might sometimes just write this, dk nu, and I'll just sort of assume whatever the other piece of data is that I need to do this, okay? All right, so this is what's going to kind of allow me to do all of these things at once. The notation isn't precise, but it's extremely convenient. Okay. Okay, so this gives then a uniform structure for the set of C nu mappings from M into M. Okay, so using this, one can show so there's some facts. Okay, so this actually doesn't really require the uniformity to say this, but it's easy to see using the uniformity that these spaces are Hausdorff. Okay, so to prove Hausdorffness, what you have to show is that given any phi and psi, there exists some semimetric which discriminates between them. Okay, that's relatively easy to do. Okay. Okay, it's complete. Okay, so if you have a uniform space, you have Cauchy sequences, and the Cauchy sequences are defined by asking that the Cauchy condition hold in each of the semimetrics. Okay, and then you have convergence. Convergence means that convergence holds in each of the semimetrics. Completeness means that Cauchy sequences converge. Okay, so the uniform space description makes that statement make sense and makes it so you can prove it. So these spaces are metrizable, except in the real analytic case. In the real analytic case, they're never metrizable. Never, regardless, unless M is a point or something like that. Okay. All right, so how do you prove something like this? To prove that it's not metrizable in the analytic case is absolutely non-trivial. Okay, and I will say nothing about it. To prove metrizability in the cases where it is metrizable, you use the fact that if you have a uniform space that can be described by a countable number of semimetrics, then it's metrizable. That's the standard construction, and I kind of gave you the formula. Right, we talked about that before. Okay. And this is separable. Okay. All right, so this uniform description gives you some nice attributes. And again, you don't need the uniformity to do all of this, but it's certainly convenient to do certainly these two. Okay. All right. Okay, so now we will specialize. What time do I have?
9:52.
Okay.
So we have metrizability for the homomorphic case,
Yeah.
but not for the real analytic.
Yeah, and that's because the neighborhoods are not countable. Right, so when you had that initial description, well, the final description for the topology, I had these neighborhoods of M and M bar. That directed set of neighborhoods is extremely complicated. Yeah. But I should say, even in the compact case, even when M is compact, and that set of neighborhoods, for example, will then have a countable cofinal subset. Okay, even then, it's not metrizable. Yeah, so this space is only metrizable in basically dimension M equals 0. Yeah.
The passage from homomorphic to real.
Yeah, it's complicated. Yeah. That's one of the, and one of the interesting things is it doesn't matter. But that's the fact that it doesn't matter is non-trivial. Yeah, because all of the stuff you know about metrizability is you have to find something else to stand in for metrizable. Yeah. Okay. So now what we want to do is just very quickly adapt all of this stuff to looking at topologies for spaces of sections of vector bundles. So I will do that. Then we will go back to talking about topologies for spaces of mappings, and I will give you a third description of these topologies. Oh, so I should say that okay. So again, in the analytic case, I have not proved that these semimetric topologies agree with the other two topologies. So now we have three potentially different descriptions of the topology for the space of real analytic functions. We had the final topology, the initial topology, and now we have the semimetric topology. I'm imagining that those are all three the same, but it actually hasn't been proved yet. Okay? So I will just say it this way, except possibly, but not likely. Okay, this shouldn't be deep. Okay, the uniform topologies agree with the other descriptions. So in all the other cases, that's established. Okay, but in the analytic case, we don't know. Okay, all right, so let's think about vector bundles. So in the case of a vector bundle, so this is going to be okay, so remember when we talk about manifolds and vector bundles, we're going to think about regularity classes, infinity, smooth, analytic, and holomorphic, okay, depending on the degree of regularity that we're interested in. Okay. All right, so what I will do, so for the vector space, gamma nu, so these are the C nu sections of E. We define a locally convex structure by defining seminorms. And these seminorms are just going to be elementary adaptations of these semimetrics. Okay. In fact, the seminorm, this case is the first case that Sauber and I looked at. Okay. And then after that, I thought about manifolds and spaces of mappings. So these kind of came first. And again, in all cases except the analytic case, these are classically known. So again, I apologize. My news end up looking very much like ours. Okay, so the seminorms. Okay, and I'll use the same kind of notation for those, except P instead of D. So if I take a section C, okay, all right, so now on GM here are the fiber metrics for this vector bundle. Okay, so I have a vector bundle now, JM over M. Okay, and I had established that this is isomorphic as a vector bundle. To that, I hadn't established that, but I told you that I did. Okay, and so now when I write GM, I mean the fiber metrics on this vector bundle. Okay. Okay, and just like in the case of mappings, I used, for each compact set K, I have two seminorms, okay? PK are exactly these ones, okay? And then you have one defined using dilatation. And I will just say, without going into it in too much detail, that you can actually, because now we're talking about sections, you can actually describe the dilatation explicitly, okay, using covariant derivatives. Right? So I won't give you that development, but in the vector bundle case, these seminorms do not require you to use the Kuratowski embedding theorem and all of that stuff that we developed last time. There's a more direct definition of these seminorms. Okay? All right. And just like in the case of mappings, you define seminorms here by taking this exact definition and doing it for every m. Okay. And in the holomorphic case, you just take the C0 seminorms. I shouldn't have erased that because I could have just adapted it. Okay, and then in this case, P, K, A, omega. Okay, so K is a complex subset, A is one of these sequences of positive real numbers converging to 0. Yeah, sorry, so this, J, oh, sorry, I forgot the A. So A is 0, A1, AM, JM, CX, JM. Take the soup of that over X's and K and positive integers M. Okay? So those are your seminorms. Okay, so maybe some history here is worth getting into. So in the case of functions, okay, I gave you two different descriptions of a topology for the space of real analytic functions, and then I told you that this chappie Martineau proved that those two descriptions agree. From neither of those descriptions, okay, can you deduce seminorms for those topologies? Okay, so in other words, what I'm saying is neither of those descriptions just immediately lead to natural descriptions of seminorms. Okay, so the first appearance of things which were related to seminorms like this came in 1984, and I forget the guy's name. Do you remember his name?
Mujica?
Yeah, say it again.
Mujica.
Oh, Mujica, that's right. So, okay, so he looked at topologies for spaces of germs of holomorphic mappings, and he came up with some seminorms in that case. Then in the real analytic case, the first proof I know of that things like this are seminorms for these topologies was by Vaught in 2013. Okay, although it was mentioned, I saw it just mentioned without proof. Paper of Damansky in 2010, not paper with some lecture notes. Okay, but the first actual proof I saw that, again, things like this were seminorms, really I didn't see till last fall, or 2 falls ago, time flies. Okay, but even then there's still some work to do because these seminorms that I'm using here come using connections and metrics for vector bundles. This result of Vaught is defined in a non-geometric setting, so he's talking about topologies for spaces of analytic functions on open subsets of Rn. So to really prove that these things are seminorms for the real analytic topology on the space of sections is a ton of work. Very difficult to prove that these constructions right here, okay, the constructions of these things give you what you want. Okay, that's hard. Okay, and that's where those j factorials come in. That's false without those. Okay.
Can you give some justification as to why you have this sequence of numbers which goes to 0? It looks like a...
Where like try to explain to you where that comes from?
Or why not just give the sequences here rather than giving a product of those sequences?
Yeah, so there's various ways you can arrange these things. And I think that a definition like you're talking about is also possible, but I kind of forget. So there's alternative ways. I mean, these are not unique seminorms, right? These seminorms work. But I think even in the paper of Vaught, his description is not exactly this. But in his description, it's a little bit different because he's working with Euclidean spaces. He has the derivatives, so you can just normally you have an nth derivative, right? But now I really don't. All I have is the m-jets, and the m-jets contain all of the derivatives, right? So I kind of think actually that for this description, this is maybe the most natural one and maybe the only one possible. But I'm not sure about that.
It seems to me something which is going to be complete with the factorials.
So let me tell you what you have here. So what you have is if you have, and I hope I can remember this. So if you have an open subset U of Rn and an analytic mapping like this, okay? The real issue here is the growth of derivatives, okay? So what kind of properties do the derivatives have? So if you take a compact set K in U, okay, then what you have is that these guys, so dk f of x, so the kth derivative, the normal, second year analysis kth derivative, okay, satisfies a bound like this. So it's, there exists a little r, okay, a constant c, so that an inequality like that holds for every x and k. And conversely, okay, if an inequality like this holds for every compact set, then f is analytic, okay? And so this r to the k is very much related to these things, okay?
Factorial should go upstairs,
Yes,
right?
upstairs are k in the down.
Oh, is it, I have it backwards? Okay, that's exactly like something I would do. Like that? Okay, yeah, thanks. Okay. Yeah, so these things are kind of, their appearance is reflected by that. I will just say it that way. But these things have, these converge to 0, and so you can see kind of convergence to 0 because if r is small, then it'll get, but none of these things really remove the fact that really to prove that these are the seminorms, there's some other stuff you have to do which is really not trivial, but it's suggested by that derivative estimate. Okay. Okay. Okay, so that is the vector bundle case. Okay, so I've defined for, so the point is that all of this gives a locally convex topology for the space of C nu sections of a CR vector bundle E. Okay. And all of those properties that I listed there for those C nu topologies, those are true here. And this is also, the statement that I'm about to make now is also true, is probably also true here, but certainly I don't even have a remote clue how to prove that here. Okay, so properties of carry over to that, so they're Hausdorff, complete, separable, and metrizable if and only if nu is not equal to omega. Okay, and we have Okay, whatever that means, so I'll tell you what it means, but it's not really clear. This is the stand-in for metrizability. Okay, this is the key factor that allows you to do a lot of the analysis that we're going to do in this real analytic case, even though the real analytic case is not metrizable. Okay, so what this means that's the definition of a Suslin space. Okay? So a Suslin space is the continuous image of a completely metrizable space. And so what you get to relax here is metrizability. So the continuous image of a metrizable space is not necessarily metrizable.
So it becomes kind of a substitute for metrizability by bringing using the metrizability properties of the preimage.
Yeah, so it's really, I guess at the core, that must be what's going on, okay? But it really turns out, so where does Suslin come up? Suslin comes up in mathematics. So Suslin comes up when people are studying radon measures on topological spaces. So if your space is Suslin, then the space of Borel sets, turns out, has some very non-trivial properties, which I guess, I'm no expert on this, must be derivable from that fact, but in a not completely obvious way. Yeah, and there's all kinds of other attributes of Suslin spaces, which I guess really come from that, but it's not just, it's 20 pages. It's not half a page. Yeah. So there's something really non-trivial kind of happening here as well. Okay, it's kind of standard stuff. It's really you will see this in kind of advanced books on measure theory. Okay. All right. Good. So what time am I at now?
15.
15. Okay. Then I will. Actually, I'll finish this today. Okay. Because it's very simple. There's an alternative description here of these topologies for spaces of mappings. Here's how it goes. Okay, so, yeah.
So for this specific case, the completely metrizable space, are we going to use the holomorphic?
No. You use the fact that this is Suslin, and so there's no fixed example of a completely metrizable space that you're using here. You use the properties of Suslin spaces.
Okay.
Yeah.
And how do you prove that that's Suslin?
It has, right, so there's two steps, okay? You fix a compact set K, okay, then we had the space of holomorphic sections about K, all right? That's the direct limit of, in fact, metric spaces, complete metric spaces. So the direct limit of metric spaces is metrizable. Sorry, is Suslin. It's not metrizable. Okay, so that's one thing. And then remember, then you have to do a compact exhaustion. Okay, so you have an inverse limit of Suslin spaces. That's also a Suslin space.
So in spirit, it's what?
It's in spirit. Yeah, where spirit means virtually everything. Yeah. It comes from the fact that the holomorphic things are Suslin or metrizable, in fact. But they only would have to be Suslin, in fact, for these arguments.
And then the limits are Suslin.
Yeah, so you have some finality properties of Suslin spaces. Yeah.
But I think the direct limit should be countable.
Yes, that's right. That's right. So it's key there that in the compact case that direct limit you take is a countable direct limit.
For
Yeah,
non-countable,
yeah.
you can say that the direct limit of non-countable
Yeah.
is just me.
Yeah. Okay. Okay. So let me quickly just finish this because it's not hard. Okay, so what we're going to do is we're going to give another description of these topologies. So I fix a regularity index in my set of regularity indices for mappings. I fix an R, which is the regularity of the manifolds. Now I take a function of class CR, okay, not C new, CR. Okay, so I define a mapping, and I call it PBF, and this is a mapping from CR functions on N to C new functions on M. Okay, it's the obvious mapping because PB stands for pullback. So it takes a function, oh, sorry, do I have this right? Oh, no, I apologize, sorry. This is a mapping from C new M N into C new M. Okay, I think I have that right. Okay, so what it does is it takes a mapping phi and it maps it to that function. And so I have this wrong. This is on N. Okay, so F is CR. Okay, but these guys are new. Okay, but this is a well-defined mapping. All right, so so now I have a mapping like this for every F. Okay, and so I have an initial topology here defined by this mapping for every F. Okay, so there's one case where it may not. That's in the real analytic case, and there's one case where it does not. In the real analytic case, again, it should not be a deep result that it is true, but it hasn't been proved yet. Okay, so I have this where there's still some work to do, and there's one case where it's for safety, I think I'll require both of these to be Stein. Okay, so in the holomorphic case, it's not only do I not know that it's true, I know that it's false in general. Okay, if M and N are Stein manifolds, you're good. Why does Stein come up here? Stein comes up because in case these holomorphic manifolds M and N are Stein, they can be embedded into complex Euclidean space. And then, and more importantly, what this implies is that in any neighborhood of a point in a Stein manifold, you have coordinate functions that are globally defined holomorphic functions. That's the crucial thing here. So, and basically that's the crucial thing for all of this, because what are you going to do? You're going to choose your functions f here to be coordinate functions when you kind of establish the equivalence between these topologies. Okay, so the existence of globally defined CR coordinate functions is crucial for this equivalence. And so that holds in the C omega case, but I just haven't finished the proof that these topologies agree. And in the, in the analytic case, and then in the holomorphic case, it's just not generally true. Okay, so this is a third description of these topologies. Okay, so
what is not true is the fact that you cannot find those coordinate functions. Or?
That's good. Yeah, both of those things are true. In the non-Stein case, you're not guaranteed that you have globally defined holomorphic coordinate functions. Yeah, that's one of
Spaces
the.
are always separable, right? In this.
Yeah, yeah. The ends in the ends.
Yes.
Yeah, they're nice. They have all the properties of Euclidean space. Yeah. Okay. All right. So now we have 3 descriptions of these topologies. Next time I'll give you a 4th one using, for those of you who like this stuff, coordinates. Okay. So we'll give sort of a more concrete description of these topologies. Okay. That's it for today.